is my set. Again, we can discuss with you the idea of linear dependence and linear independence, and we can discuss with you the manifestation of those two ideas in case of two vectors specifically. Here's my discussion. I'll start it different. Let's just assume this set is linear dependent, just for a second. Let's just see what sort of turn it will take if I apply the definition of linear dependence in this case. So what does it say? The definition says that I can produce two coefficients, lambda and mu, such that the moment I such that the linear combination of my vectors will be zero, even though lambda and mu are not simultaneously zero. One of them for sure is not zero. This is the definition of linear dependence in case of two vectors. Let's just see what it gives us. Because I can rely on this fact that either of them is not zero, what I will do, I will just try to consider these two possibilities. We'll just consider the possibility lambda specifically not zero. If it is so, then I can solve for x, right? It's here. If lambda is not zero, I can divide words by lambda. So I can take this relation, rearrange it a little bit, and solve it for x. And that's the kind of relation I'll have in case lambda is specifically not zero. And that is the relation which tells me that one vector, when we know one vector is a scalar multiple of the other, geometrical manifestation of this fact is that one vector is parallel to the other. What happens if mu is not zero? If mu is not zero, then I can do a similar thing, but now with respect to y. I can divide by mu, so I can solve for y. And again, I have one vector is a scalar multiple of the other, which means, again, x is, in geometric terms, x is parallel to y. X is parallel to y. And this is the manifestation of this original assumption. We assumed, or I should say I assumed, that, that my two vectors as a whole, as a set, is linear dependent, and I just proved right here in these two lines, it's a official formal proof that such vectors will inevitably be parallel. In fact, the opposite statement is also true. If you assume vectors are parallel, if you assume that that one vector is scalar multiple of the other, if you assume they are parallel, hence one is the scalar multiple of the other, you can take this relation I just typed and you can rearrange it into the following relation: 1 times plus minus lambda times into this. So I made an assumption that my vectors are parallel, hence one is a scalar multiple of the other, and I just slightly rearrange this assumption into what? Into a linear combination of x and y with the coefficients 1 and negative lambda. And I can be sure that one of these coefficients is not zero, right? One is certainly non-zero. Hence, they are linearly dependent. That's exactly the definition. So this is the opposite proof. So now we basically proved with you the following, very formal, and we've done this very formally, that in case of two vectors, linear dependence is equivalent to vectors being parallel. This is the geometrical interpretation of linear dependence in case of two vectors.